All right, last time we looked at elastic potential energy. Essentially, if I have a spring, I'm actually going to scroll down here. So I'm going to actually diagram this out here. So I have a spring. We're going to say we're going to put a ball on it, okay? And we're going to say once we put a mass on it, we're going to say we put a, we're going to say that this ball has a mass of, let's go with 50 milligrams, or no, we're going to say 50 grams or 0.05 kilograms. Okay. When we put it on this spring, it compressed it. So we're going to say that it started here, moved down to there, and we're going to say that that change in distance was 0.1 meters. Okay. This spring had a spring constant of 10 newtons per meter. And my question is, how high will the ball go when the spring is released? All right. So really what we're going to see here is the whole reason why we learn about these potential energies is so we can see how they kind of transform in between each other, how they get transformed into kinetic energy. Later on, we'll probably look a little bit into how do these things become chemical or thermal energy, electromagnetic energy, anything like that. The whole purpose of energy is, or the way that we're going to look at energy is how do I actually get it to change from one form to another? Because like we can see this with our pens. If I click it and hold it down, when I release it, my clicky pen will jump up. And we should be able, if we know that spring constant, we should be able to calculate just how high that thing will go. So right here, I've stretched it downward. I've given it some amount of elastic potential, which I already calculated last time. I know that at this point, the elastic potential energy is equal to 0.05 joules, okay? When I release this ball, it's going to move up to a certain height. We're going to look at this in an idealized world. Essentially, there's no energy loss from stretching or compressing, kind of a elastic friction, if you will. We're not going to lose any energy to air resistance or friction or anything like that. In an ideal world, the amount of gravitational potential energy here should equal the gravitational, or I should say the elastic potential energy here should equal the elastic energy up here. Because if this energy is just changing form from one to another, all of this elastic potential should become gravitational potential. So these two things should be the same. I let the spring go, all that energy gets transferred to the ball, becomes gravitational potential energy as it's flung up into the air, assuming, it's aimed straight up, perpendicular to the ground. All right, so now I have GPE is equal to 0.05 joules. So now I just need to go back and figure out, well, what's the formula for gravitational potential energy? I check my note card and it looks like it's mass times acceleration due to gravity times height. Now for the question, I want to know how high will the ball go? I'm looking for height. Um, I know the mass is 0.05 kilograms. I didn't say where I'm at, so we're going to assume we're on Earth, so I know acceleration due to gravity is 9.81. So I have 0.05 joules is equal to 0.05 kilograms times 9.81 meters per second squared times height. I have to get height by itself. So essentially, I'm just going to divide both sides by 0.05 kilograms times 9.81 meters per second squared. Those will cancel. What I do to one side, I have to do to the other. Try to write a little bit smaller. All right, so this tells me exactly what I need to do. So height is equal to 0.05 joules divided by, just write a little bit neater over here. I'll put that there. All right, so that's what I need to type into my calculator. So get that up. Let's clear that. Drag it over. So I got 0.05 divided by parentheses 0.05 times 9.81 close parentheses equals I got this will reach a height of 0.1 meters, or 100 centimeter, 10 centimeters, 100 millimeters, anything like that. That's actually probably not bad. That's still maybe a little bit too high for use in a pinball machine, where the difference between like the top of it and the like bottom part probably isn't a difference of zero point 0.1 meters, but it's not a horrible number. It's not too far off the base. So energy changes form from one to another. Another way to look at it is, let's say that I have up on a cliff, I have a, let's go with an 8 kilogram bowling ball. Okay, 8 kilogram bowling ball. It's on a cliff that's 15 meters tall. Okay, we're on Earth once again. So up here, it has a certain amount of gravitational potential energy. My question is what velocity will the ball, let's give some ground there, hit the ground with? Right, because it's starting off up here where all it has is gravitational potential energy. I'm even going to put the little knot sign. That is my, actually not a knot. I'm going to do this a little bit differently. That's my initial gravitational potential energy. Okay. So we're going to kick the ball off and it's going to hit down here. Down here at the bottom, once it's on the ground, my final gravitational potential energy is 0 joules. All right. Up here, when my ball was on the cliff, essentially it had no joules of kinetic energy. It wasn't moving. Oh, better put my I here to indicate we're talking about initial kinetic energy. We kicked it off here though. My final kinetic energy should equal my initial starting gravitational potential energy. In this case, what we're going to find is if I knock this ball off the cliff, all of this gravitational potential energy has been turned into kinetic energy. Once again, idealized world, there's no air resistance or anything like that. Okay. The big takeaway here, though, is my final kinetic energy is going to be equal to my starting gravitational potential energy, because energy just changes from one form to another. So the moment before it hits the ground, or the moment it hits the ground, I can figure out what its kinetic energy is if I can find the gravitational potential energy. So my initial gravitational potential energy, mass, acceleration due to gravity times height. We said it's an 8 kilogram ball. Acceleration due to gravity is 9.81 meters per second squared. Height, we said, was 15 meters. All right. So gravitational potential energy, get that out. We have, let's do that, 8 times 9.81 times 15. All right, so we have 1,177.2 joules. All right, that's how much gravitational potential energy it had sitting on the ledge of the cliff, okay? Then it got kicked off, and all of this GPE becomes kinetic energy. So essentially, I know my ending kinetic energy, 1,177.2 joules, okay? If I'm making my diagram complete there. So now I know if that my final kinetic energy is, 1,177.2 joules, and I know the formula for kinetic energy is 1/2 mv squared. I can solve for v squared by itself. First step is to divide this stuff over, so v squared is equal to ke. Dividing by 1/2 is the same as timesing by 2, divided by mass, so now I just need to take the square root of both of these. velocity is equal to the square root of ke times 2 divided by mass. All right, I know the mass. The mass of this boulder hasn't changed from its fall. The kinetic energy we already figured out. So V is equal to square root 1,177.2 joules times 2. Stand my square root out. Over the mass we said was 8 kilograms. All right, let's get this guy over here. Times 2 divided by 8. I'm going to write this down real quick. So really we're taking the square root of 294. If I remember right, I saw 0.3. Yep, okay. So now I just need to take the square root of that. That doesn't look right. So let's go square root. No, there we go. Square root 294.3. Square root equals 17.155. Sounds good. All right, so now my unit though is velocity, and velocity we should know at this point is meters per second. So my 8 kilogram bowling ball boulder, whatever it was, I kick it off of a 15-meter tall cliff or ledge, something like that. All of that GPE becomes kinetic energy. From there, I can figure out using the kinetic energy equation that the velocity, the moment it hits the ground, 17.155 meters per second. So that bowling ball is moving very, very quickly. And that's why it would hurt to get hit by that. All right, so with that, that's kind of a good basic introduction into kind of mechanical energy. The fact that these energies change form, going back to like the pinball thing, the spring constant one, we could have gone from elastic potential energy. We could go from there to figure out how much kinetic energy does that ball have the moment it leaves the spring, figure out what velocity that ball's at, and then from there figure out, well, how tall does it get? I think the cool thing about it though is we're able to do all this calculating without having to touch those kinematic equations at all. So I think using the energy equations tends to make this a lot easier and straightforward to do because just one type of energy becomes another. But it does have some limitations. Other than that, good luck with the practice. Have fun.